Good afternoon and welcome to the Bulkley Valley Research Center virtual seminar series for January 26, 2022. It's great to have you all joining us today. We're super excited about this topic and this presentation from Matt, and much appreciation to you, Matt, for your time today. I'd like to acknowledge that I'm hosting this seminar from the traditional territory of the Gidimt'en clan of the Wet'suwet'en Nation. I'd also like to acknowledge our funders that make it possible for the Research Center to host this seminar series: Wet'suwet'en Community Forest Corporation, Bulkley Valley Community Foundation, and Bulkley Valley Credit Union, and of course, all of you that have purchased a membership. It's great to have your support and your interest and to be able to connect with you more directly through our information bulletins and our emails out about seminar series, and your support for the center and enabling our seminar series and other activities such as this to happen is greatly appreciated. If you have any questions or concerns, please don't hesitate to be in touch. My name is Dawn Hansen and I'm the Executive Director of the Bulkley Valley Research Center. We have presenting to us today Matt Beedle. He's a professor of geography at Coast Mountain College in Terrace and an adjunct professor of geography at UNBC. His PhD research at UNBC focused on glacier change in relations to climate variability in the Caribou Mountains. And currently he's investigating the impacts of a changing climate and melting glaciers on stream temperatures and salmon in subdrainages of Kitsimkalem, Meziadin, and Morice Rivers. And we're thrilled to have you with us today, Matt. Thanks so much for joining us.
Awesome. Thank you so much for that intro. Dawn, can you give me a thumbs up? Can you hear me okay? Okay, cool. Great. Thanks so much for all of your interest. Really happy to have a crowd here. Hopefully I can live up to your expectations. I want to start by acknowledging that this work it's a partnership with a number of different groups, and it was initiated by the Skeena Fisheries Commission. And this work in particular on Morice is also in partnership with the Morice Watershed Monitoring Trust. So thanks for their partnerships. I would also like to acknowledge that I'm coming to you today from the traditional unceded territory of the Tsimshian people of Kitsimkalem here in Terrace, where I live. And it's a great privilege to be here, to live here, to play in this beautiful country. Additionally, I'd like to acknowledge that all of this work that I'm going to share with you takes place on unceded traditional territory of the Wet'suwet'en people. And while none of this work was actually on the ground, it's all through remote sensing and modeling. I have had the privilege to spend some time in the Nanaka Kid Price area, and it's an amazing area. And I hope that this work can be beneficial moving forward in terms of decisions around management of a really important watershed. So where we're going today is I'm going to share with you a snippet of some larger research that's been going on for some time now. And so what I begin sharing with you, these are components of a larger project. So I'm involved with the Skeena Fisheries Commission looking at this bigger picture of climate, glaciers, and impacts on water and salmon in both Morice, the larger Morice area, Morice River watershed, and the Meziadin watershed. And for each of these locations, I'm finishing 3 reports. I've finished the first report and the second report for each location, and I'm wrapping up the third. So what you're going to see today is a little bit of information from that first report where I talk about the importance of topography and land cover on water, both water discharge and on stream temperatures. The next one I'll get into today talks about a recent glacier inventory and glacier change going back to 1975. So what's happened historically and where we are today with respect to glaciers and impacts on water. And then the third part, which will actually be the brunt of the presentation today, is what I've been wrapping up, and I'm currently finishing these reports as we speak, and excited to share some of those first results, modeling what we can expect to the end of the 21st century. So a little bit of a dive into where we're looking today. So just a Google Earth image showing our region. I'm over there in Terrace. Most of you, I believe, are in Smithers, but some of you are in between and elsewhere. And we are focusing on these drainages in the upper Morice system. So these outlines in blue here. And not the entirety of the Morice watershed, but think of it as the dominant major high elevation watersheds contributing to the Morice River. And another image of these drainages. So we're going to be looking at a number of smaller drainages, the larger drainages at the high elevation reaches, so Atna Lake, Nanaika River, feeding into Morice River, and then also a number of smaller surrounding watersheds that have been identified as important as trout, salmon, steelhead bearing streams in the upper Morice as well. Now, before I begin, I want to kind of throw a caveat out there, and that is that salmon are facing a myriad of challenges, and climate change is only one of them. And so while I do make this connection to from climate to glaciers to salmon, know that it's not the only thing, but it is an important one. And so hopefully this will shed some light on one of these particular challenges that salmon are currently facing and will be facing in the coming decades. All right, I'm going to start by a little motivation for why are we concerned? Why are we interested in the impacts of climate on water and salmon? So I want to start off with a bit of a hopeful note. And there is a lot of science out there showing that salmon populations do show great resilience. And if we don't push them too far in terms of the magnitudes of change that they're going to experience and the rates of those change, they should have the capacity to respond. And there are different ways that they can respond. But there are lots of studies showing salmon populations have great resilience. And so a bit of a hopeful note there. We do have a number of impacts related to climate change. So one is increase in thermal stress. This impacts spawning migration, spawning, rearing, etc. This then, when you have a warming stream system, warming aquatic ecosystem, you give the advantage to warm water predators potentially as you move above these certain species assemblage thresholds. And this is predominantly impacting or can predominantly impact those stocks and species that spend more time in the freshwater environment. So sockeye, coho, and chinook. They have this greater exposure to potential thermal stress as they live more of their life cycle in the freshwater environment. But also there could well be increased aquatic food web productivity as you get a greater growth response with higher temperatures. With climate change, with receding glaciers, with changes in seasonal snowpack, you have reductions in volume of summer and fall flows, or summer and fall discharge. So you get reductions in your discharge, and this can have impacts on access to spawning habitat. You also get an increase in intensity and frequency of winter flooding potentially with climate change. As temperatures go up, as you maybe get more winter rain events, more winter melt events, you can have winter flooding leading to scouring of redds and eggs. And then this melt timing, seasonal snowpack impacts also have potential impacts on seaward migration timing, which are important. So a number of things there that relate to these potential impacts on salmon from climate change. Now, to also put this in context and why I'm interested in the projects I've been doing is that we have some pretty good information from a few different locations up and down the Pacific coastal temperate rainforest. And further to the south of us, we have many streams that are already experiencing thermal stress. And so this quote comes from a paper by Nathan Mantua from a number of years back, but in Washington and Oregon, you have higher temperatures and generally already episodes of extreme thermal stress. Counter to that, further north than us in the Juneau area, where you have much larger glaciers, you have glacier coverages there of upwards of 60% of basins being covered by ice, and there your temperatures are actually below the optimal thermal range for salmon. And so one conclusion out of some recent work is that reductions in glacier meltwater actually might enhance salmon survival and growth in some watersheds. For the Skeena River, it's a bit of a question mark. There isn't as much work. And so I've done some work in the Kitsam-Kalem, subdrainages of the Kitsam-Kalem, and now the the Morice, and also in Meziadin in the Nass system. So all of these basins up and down the Pacific coastal temperate rainforest are unique, and they're all going to respond slightly differently. But we don't really have a great picture of what that looks like here in the central coast of British Columbia. All right. I'm going to start by sharing a few basic introductory or foundational things that provide information of what we can expect in these watersheds. And the first one is topography. Topography is really important when it comes to climate, thermal regime of your aquatic ecosystems, and really lays the groundwork for what you have. So first we have these two lower elevation watersheds, Lamprey Creek and Owen Creek. So far lower in elevation, generally warmer, less seasonal snowpack, and generally lower slope angle. So I include slope angle here, and you can think of that as a metric in terms of residence time for water in the watershed and how much opportunity there is for water to warm before it flows away. Then we have two additional watersheds, so Gosnell Creek and Thotto River, a bit higher in elevation, a little bit steeper as well. And these two I've separated out as they don't have glacier cover. So they're higher in elevation, but they don't have glacier cover. I should note there is one remnant glacier in the upper part of Gosnell Creek that I found on the recent inventory, but it's really small. Then we have the larger watersheds to the southwest, higher elevations, and that's where all the glaciers sit that feed Morice River. So you have Atna Lake and Nanaka River. And those two, Atna Lake, Nanaka River, and then this central area in the middle that feed directly into Morice Lake. This area drains into Morice River. So those, the topography there is really important for setting the stage. I go further in the reports talking about the importance of topographic shading, which is also critically important. Also thinking about north-south ratios in terms of snowmelt capacity for these different basins as well. Next, in that first report, I went into the basics of land cover. So on this figure here, you have a few different things that indicate land cover, important land cover that relates to streams, stream temperature, stream discharge. So in that reddish, orangish, brownish color, those are clear cuts. And then you have this blue stippled area you can see along the southwest margin. That's your glacier cover. You also have lakes in the blue color, and then as well there's a cross-hatched pattern there indicating wetlands. So a number of different things that are important in terms of land cover shaping stream temperature. So for those lower elevation sites, the really biggest thing there is clear cut percentage, and in up to 50% area being clear cut in terms of Lamprey Creek. So these lower elevation sites, they're more accessible, lots of logging in this area, and that will have an impact on your stream systems. Less clear cut area in Gosnell and Thotto River, and less lake cover as well. And then the big ones to the southwest is where you have the bulk of your glacier cover and also your large lakes. So Atna Lake, that drainage, about 10% glacier covered. That's by far the most glacier cover in the larger Morice area. Nanaka River, about 2% glacier cover, nearly 6% glacier cover. And then if you look at the Morice River as a whole, so that's Atna Lake, that central Morice Lake area plus Nanaka River. That area accounts for, it's 3.5% glacier cover and 8% lake cover. And why this matters, it matters for a number of reasons. So when we think about the importance of forest cover, we have the importance of riparian shading. So canopy shading stream environments, keeping streams cooler than they otherwise would be. I don't get into that here and can't from a satellite perspective, at least from the resolution of Landsat. I can't really say what the impacts are. Many of you on the call would know far more than me on that, but it would be an important thing to get a handle on, especially in these heavily logged basins. However, one thing that is important that I will get to is how forest cover impacts snow accumulation and melt. So there's quite a bit of research going back many decades showing that this interception effect, so snowfall that lands on a tree and then is available to sublimate or evaporate, dramatically reduces the amount of snow that falls to the forest floor. And so that's roughly 40%. You can have up to 40% less accumulation in a forested area. But then you have melt rates that are 70% lower in those forested areas. Counter to that, so if you think about it from the perspective of a clear cut, you can get up to 40% more accumulation, but then you have that rapid melt off in the springtime, which can really affect the magnitude and timing of the freshet. Lake cover is important as it imparts a warming influence. So it increases residence time within the system, increased exposure to solar radiation. And then glacier cover, which we're going to dig into more deeply here. Meltwater in late summer and early fall, that's your melt season. That's when your glaciers are contributing to your streams and rivers. And this provides a thermal buffer and also maintains discharge. So a number of reasons why we're concerned with land cover. You'll note that I did neglect to include wetland areas, and that's because they're quite marginal in these in the Morice system. I think the maximum was about 2% wetland cover in the Atna Lake Basin, and that will have a slight warming influence, but it's not a significant component, or likely won't be a significant component. All right, I'm going to dive into the glaciers and recent glacier change. So this is from the second of the 3 reports. And before I do that for Morice, I want to put glacier cover in context for the larger Skeena. So this data on this slide I'm sharing with you is from the 2005 glacier inventory completed by Tobias Bolch and others at UNBC. And it was the first really conclusive inventory, recent inventory of all of Western Canada. And what they found was about 1.5% glacier cover in the Skeena, and Morice River, about 86 square kilometers as of 2005. It represents about 10%, a little more than 10% of the total glacier cover in the entire Skeena. So when we're thinking about the Morice as a component of the larger Skeena, just keep that in mind in terms of the magnitude of ice we're talking about in the larger Skeena. So looking at the Morice today, it's about 10% of the larger Skeena basin. All right, so what I'm going to share with you now are some recent glacier change data, as well as a recent 2019 inventory. And these are based off of early July 1975 aerial photos and manual glacier mapping that the province completed. And then the 2005 glacier extents, those are the ones mapped by Tobias Bolch in the data that I just showed you. And then I completed an updated 2009 inventory, current inventory from Landsat 8 imagery. So before I get into the results, I want to talk about some of the types of data that I'm going to be sharing with you when it comes to glaciers and glacier change. First of all, I'll share with you absolute glacier change. So that's in terms of what are the actual changes in square kilometers. All right. And so, for example, in 2019, Atna Lake, the glaciers in the Atna Lake drainage have 27.8 kilometers squared of ice. And since 2005, they lost 6 kilometers squared. So that's an example of an absolute change. But more often, what we're going to be looking at is relative change. So in terms of relative to the relative to the watershed area. So that's really critical in terms of how important those glaciers are to the watershed. How much are they contributing to discharge? So for example, the glaciers of the Atna Basin are about 10% of the surface area of that total basin. And then we can also think about it in terms of relative to a previous glacier surface area. And I'll share with you some numbers that are relative change. So from 2005 to 2019, the Atna Lake glaciers lost about 17.8% of their 2005 surface area, or at a rate of about 1.27% per year. So just an idea of some of the different stats I'll share with you for glaciers and glacier change. All right, I am now going to be focusing completely on the basins to the southwest, the ones that do have present day glacier cover. And those include Atna Lake. And then I'm terming this middle section here, Morice Lake. So this is the part of the Morice River watershed that is not part of Atna Lake and not part of Nanaka River, but are smaller drainages that feed directly into Morice Lake. And then those three combined are your basins that feed Morice River. Here's an image of the entirety of Morice River and the glaciers that are present. And a bit of an inventory to start out. So this is what we have present day. So in the Morice River drainage present day, we have 241 glaciers, total of 69.2 square kilometers, which represents 3.5% of the total watershed. And if we break that up by its component parts, these three individual subdrainages, Atna Lake has 50 glaciers, 28.4 square kilometers, and that represents 10.4% of the Atna Lake drainage. Morice Lake, the glaciers that drain directly into Morice Lake, there are 83 glaciers, 23.7 square kilometers, and about 2.7% of that individual watershed is covered by glaciers. And then Nanaka River, 108 glaciers, 17 square kilometers, and 2% of that watershed covered. Now, a couple of additional important things to realize here. So if you look at the distributions here, so Atna Lake has 50 glaciers at 28.4 square kilometer total, and Nanaka has 108, but only a total of 17 square kilometers. So what we get here is an interesting gradient of larger glaciers to the north and west, smaller glaciers to the south and east. And we'll talk about that more in a minute of why that is and why you get different responses moving forward. And in general, it's that the smaller glaciers are melting faster. Now looking at change since 1975. So again, we're going back to the provincial mapping from aerial photographs in 1975. And for the entirety of Morice River, 1975 to 2019, there's been a loss of 47.1 square kilometers, or a loss of about 42% of the 1975 surface area of glaciers. And breaking that up, you have about a loss of about 31% of ice in Atna Lake, 42% roughly in Morice Lake, and 55% in Nanaka River. And so there, once again, you're seeing that difference between the larger glaciers in Atna Lake losing less of their surface area, and the smaller glaciers of Nanaka River losing more. One of the big takeaways, though, from this as well is there's information from 1975 to 2005, and then 2005 to 2019. And a big takeaway here is the rate of recession has increased, and it's increased markedly. And for almost all basins, it has doubled or more than doubled. In the Atna Basin, those glaciers have nearly doubled in terms of their rate of recession. And this is also recent papers by Alex Bevington, Brian Menounos have come out and found very similar things with their recent inventory work as well. Now, when we move into thinking about the importance of glaciers and glacier change, we need to recognize the timing of when glacier melt is most important for a freshwater ecosystem. So on this figure here, you have months of the hydrologic year on the x-axis there from October through September. And then over here on the left, you have percent of annual runoff. And this is taken from a figure from the seminal paper by Andrew Fountain and Wendell Tangborn from 1985 that were really kind of the first to look at how stream flows responded to different glacier, relative glacier surface areas in a basin. And the big thing here is that when you move from a basin that has glacier cover, a glaciarized basin, to one without glaciers, the big change you see happens in late summer and early fall. So it's typically the months of July, August, and September, where you go from a system that has glaciers and maintained discharge to a basin that loses that glacial source of meltwater, and it struggles to maintain that discharge in those months, which are the dry season, which also are the warm season. So this is an estimate of glacial meltwater, the component of glacial meltwater to total discharge for the Morice River. Each of these columns is the actual discharge as measured by Environment Canada at Morice River, going back to that 1975. And then the blue component on top of each column there, that's an estimation of the glacial meltwater component. And I've estimated that based on these observations of how surface area has changed, and then observations of regional surface mass balance, or how much melt we observe in a given year. And then that's integrated over your surface area to give a total glacial component to that meltwater. And this is what it looks like in terms of the importance of glacial meltwater. And again, this is only for the July to September discharge. Okay, so just looking at that period when glaciers are most important. I then now have added, so you see Morice on the top and Nanica on the bottom. And the big takeaway here is that for Morice, going back to the 1970s, on average, your glacial component for that, for your discharge is about 10.8, 10%, 11% or so on average, but varies quite markedly depending upon the summer season. So if you have a cold, wet summer, your glaciers are happy, they're blanketed in snow, they're not melting very much, and they're not going to contribute a whole lot. That 30% figure, that's going to those last two bars. That was that drought period we had in 2018, 2019, where we had incredibly dry years, really warm, dry summers, and lots of melt. And so you see that in those dry years, when we need that infusion of glacial meltwater, we're getting a pretty good amount, up to 30% of the discharge you would have seen if you went out in 2019, 2018 to the Morice River. That would be from glacial meltwater. Now for the Nanica, it's a bit less as we have less glacier cover in Nanica River. The average is about 9% or so, and the max there in recent years was about 25% from glacial meltwater. So that's where things stand today. So that 30% and 25% kind of max capacity for buffering, for introducing cold meltwater to our rivers and streams, that's where we sit in the present day. And that's kind of reflective of the maximum amount we could receive under present day conditions. All right, so moving forward, I'm going to be going into the future for the rest of the information. And to start, I want to introduce a little discussion about climate scenarios. So when we go forward in time, when we do modeling efforts out to 2100, a lot of our potential variability, a lot of our unknown is what we as humans choose to do. And the modeling community represents this through a number of different means, lots of different climate scenarios. And you may be familiar with the representative concentration pathways, or RCPs. And these go back to the IPCC Intergovernmental Panel on Climate Change Assessment Report 5. Our fifth assessment report. And these have been used quite heavily in recent years based off of what's called CMIP-5, the Coupled Model Intercomparison Project. So that's this international body that's doing a bunch of collaborative modeling, let's say. We are transitioning, however, to new types of climate scenarios, more refined types of climate scenarios, and these are called shared socioeconomic pathways, another mouthful, or SSPs. And these are in use now. We're currently in the 6th assessment report cycle of the IPCC climate reports, and they're now relying on these SSPs. And I bring this up here because what you're going to see is some modeled results that use both RCPs and SSPs, and that might be kind of confusing. What you need to know, though, however, is I've color-coded everything. If you see a blue line, that's your RCP 2.6 or SSP 2.6. And that's basically we're getting our act together scenario, right? That's kind of the keeping global climate change to 1.5 kind of goal. Green then is we're doing okay, not as great. Yellow is we're making some progress, but it's heading in the wrong direction. And the kind of orangish reddish color is things aren't going well. So think about it that way. Happy to dive in more and discuss afterwards if you want to discuss RCPs and SSPs. It's a whole nother realm of science in and of itself, but I wanted to boil it down there and make sure that wasn't confusing. All right, so moving forward into the future. So this really provides the foundation, I think, in terms of where we're going in terms of impacts, climate-related impacts. And that's what we're likely to see in terms of temperature. Now, this data I extracted from what's called Climate NA standing for North America. And this is the ensemble of 13 of those CMIP6 global or general circulation models. Really handy tool. If you're interested and haven't used it, check out Climate NA online. What this data is for, this is for a midpoint and a median elevation for the Morice River watershed. And you've got the 4 different seasons and traditional definitions of seasons here. Winter is December through February, spring, March through May, summer, June, July, August, autumn, September, October, November. Main takeaways here are that there's a really big range in terms of where we might head in terms of climate. And again, the big unknown here is what pathway we as humanity choose to take. The big takeaway though too is that on the blue lines here, the we get our act together line, we're still looking at an increase in temperature of 1.5 or so degrees C over present day conditions by mid-century, and then stabilizing, and then take that all the way up to the orange line, and that's the kind of business as usual. We just keep on going. All right, this data table, there's a lot here. The temperature data I just showed you for these different midpoints. So 2050 here is the mid 21st century, 2090 here is the 2-decade average period at the end of the century.
There's just
Sorry, I'm just looking at the chat.
Yeah.
So a lot of data on this slide, but the main thing I want to take away from it is what's going to happen with regard to precipitation. And in general, the story is one of increased precipitation. All of our climate models are showing slight increases in precipitation. And if you boil down all of this data here on the left for mid-century or for 2050, we see somewhere between a projected 2 to 7% increase in precipitation. And then by end of the 21st century, it's 4 to 17% increase. And that 17% is a little bit of an outlier for the most extreme climate scenario. So in general, the takeaway here is pretty moderate increase in precipitation, although showing increases in precipitation. Know that these are just general seasonal averages. They say nothing about extreme weather, atmospheric rivers, things of that nature. All right, so let's move into what are the glaciers likely to do. So many of you have probably seen this figure. This is from Gary Clark and others, their work from 2015 that modeled all of the glaciers in Western North America. And they broke it down into these different regions. So you've got the coast there on the top, the interior, and then the Rockies. Super valuable, seminal work. Really important to see where we're likely to be going. However, I wanted to take this and break it down by your sub-drainages, which are, of course, extremely unique and different across the Skeena, different across the entire Pacific coastal temperate rainforest. And this is what you see if we look at the watersheds of interest here. So what I use the Open Global Glacier Model. Highly recommend checking it out if you're not familiar with it. Really powerful new tool that's gaining a lot of ground in the glaciological community and pretty user-friendly in terms of getting in there and doing some modeling for drainages of interest. So what we have here is you have year on the x-axis of these 4 plots going out to 2100, present day conditions on the left there. On the y-axis, you have volume in meters cubed, and notice that it's in a scientific notation. And so the main takeaway here, and the first three, so on the top there, you've got Atna Lake and Morice Lake, and then lower left, you have Nanaka River, and then lower right, you have Morice River. So that's all three of these combined into one. The main takeaway here is a picture of dramatic glacier loss. Perhaps not surprising given previous work, but I think it's important to break it down into the different components. So both in Atna Lake and in Morice Lake, we do have the potential for some glacier volume remaining by the end of the century under the more optimistic scenarios, but it's only a fraction of what we have today. And we really have, what we're likely seeing is dramatic glacier recession to mid-century and then tailing off as we just have those remnant pieces of ice tucked away in the higher reaches of different cirques and north-facing valleys. For Nanaka River, those smaller glaciers, hate to say it, but those glaciers they're out of balance with current climate. They're essentially doomed under all climate scenarios. Really small, unlikely to last to the end of the century. All right, let's break this down a little bit further. And this is looking at glacier surface area change. So I'm going to go back for a moment. One thing I don't like about these types of plots, and I'll go back again to the one previously, it kind of makes it look like things are stable or we're falling off a cliff in terms of glacier change, and that we're about to teeter over this edge, which isn't really the case. So this in black there, those are the surface area observations that I made and the recent inventory. And then you have the modeled projections. And this is for surface area going out to 2100 for all the glaciers of the Morice. And I bring this up for a couple reasons. One, I want to show you that the rate of change from here moving forward, what's forecasted is essentially a continuation of what we've seen over the last decade or 2 decades. That increased rate of recession is likely to continue, perhaps increase just a little bit. And then it tails off at the end here as your glaciers get extremely small and are tucked away in those north-facing high elevation basins. Another thing to point out here as we move forward and talk about impacts on water is that you see we're moving from 60%, 65% or so glacier cover in the Morice, and by mid-century moving to something that is about roughly a third of that, a quarter to a third of that. And you're going to get this commensurate impact on your meltwater. Meltwater almost all comes from surface melt, and if your surface area is diminishing, you're going to have a lot less meltwater. All right. Another modeling effort that I went into is I tried to estimate some changes in maximum snowpack. And this is based on our observations of snowpack for our region. So on the left there, you have a map of the region. So outlined in blue at the bottom right of this map, you have the watersheds of interest for the Morice River. And then up here in the upper left, these are the watersheds of interest where I'm studying glaciers in the Mesiaden. And then all of the purple dots, purple kind of snowflakes, are sites where we have snow data. And then on the right there, you have 2001 to 2021 average maximum snowpack, and defining maximum as your April 1 snow water equivalents. And this is the trend we get with respect to elevation. I did a pretty simple estimation or simple modeling, linear model based after work that Joe Shea at UMBC and others have recently completed. And what it does is it integrates a changing linear trend of snow water equivalent with elevation with the area altitude distribution of your watershed, or watershed hypsometry. And that's what's here in the upper left. Now, this is something that's unchanging and goes back to the importance of topography. Your low-lying basins, your low elevation basins, so that would be demonstrated here by Owen Creek and Lamprey Creek in particular. Most of their surface area is below, say, 90% of it is below 1,500 or 1,250 meters. And then you have your slightly higher elevation basins. None of these area altitude distributions or watershed hypsometries are what we would call biased towards higher elevations. They're not dramatically bowed upwards, if you will. In general, this leaves these basins relatively exposed to a rising snow line and changing SWE or snow water equivalent with elevation. Now, what this model does is it uses modeled wintertime temperature. And assuming that with our increasing wintertime temperature to the end of the century, you're also going to get an increase in the zero line, or that would be the y-intercept on this plot. So the dark blue line on this graph, this graph here, these are the observations, present day observations. And then each of these lines are for a different climate scenario. Assuming that as winter temperatures rise, our zero line of where we have no accumulation will also increase. And then fixing the accumulation at the max elevation as staying the same, assuming that high elevation snowpacks will be unchanging in the future. And this gives us a little bit of an understanding of where we might be going with regard to snowpack. So a couple of takeaways here. One is that your lower elevation basins are most threatened. So there here you see Owen Creek and Lamprey Creek as the two lower elevation basins, and they're more susceptible to this change. So by mid-century, you're looking at losses of 10 to 20% or so of wintertime maximum snowpack. And it's less for your higher elevation basin. So by mid-century, snowpack changes are likely to be relatively modest, perhaps 6 to 13% or so in your higher elevation basins. By the end of the 21st century, with our more optimistic climate scenarios, things are relatively unchanging. The world we really want to avoid is the one where we have these upper ranges of climate scenarios moving towards 5-6 degrees of warming by the end of the century, and that's rapidly pushing our average wintertime temperatures closer to the melting point, which of course is really critical for snowpack. And that is definitely a scenario we want to avoid. This scenario where we have 40 to 60% reductions in maximum snowpack. The last modeling effort I'm going to share with you before I move to some conclusions and wrap things up is an effort looking at changing stream temperatures. So I did a little bit of modeling of maximum weekly average temperature, MWAT, which is a common metric for relating stream temperatures to salmon physiology, salmon life cycle, in many papers going back many years. And this looks at a number of different features of basins, the climate of those basins, and then also some of the land cover that we know is important for thermal regime of streams. So things like July, August air temperature, your catchment area, your mean elevation, glacier cover, lake cover, metric for your mean annual flood or your discharge. And this is based off of, or it is from Dan Moore's work from 2013, and also work that was used in studies provincially to find temperature sensitive streams. Now so what I did is everything in the model is left unchanged in terms of catchment area, mean elevation, lake cover wasn't changed. What I did change, I used the climate NA output to model future July, August air temperatures, and then the open global glacier model to model future fractional glacier coverage. And so those are the two things that are impacting this future maximum weekly average temperature you're going to see. Now, before I share it with you, I want to put a caveat out there. More work by Dan Moore's group has shown that these types of empirical models might well be underestimating the response to climate warming. So just a caveat, I put this in here because I want to get some idea of where we might be heading in the Morice in terms of stream temperatures. I've asked around and I'm unaware of monitoring of stream temperatures. Perhaps some of you on the call know otherwise. But in lieu of that, I wanted to share some modeling to share where we might be. And I include data here for Atna Lake and Morice River. So, and these are the two extremes. Atna Lake staying the coolest with the most glacier cover, Morice River warming the most with relatively low glacier cover, large lake areas. And again, you have the 4 different climate scenarios. Maximum weekly average temperature is on the y-axis, year on the x-axis. And to put this in perspective, I wanted to put some critical thresholds, thermal thresholds in here from other work. So Parkinson and others used the same model from Dan Moore to look at these species assemblage thresholds. At which temperature thresholds do you have marked changes in which species are dominant? And so this middle zone here, so above say 10.5 degrees C and below about 19, 18 degrees C, that's your happy place for salmon in general, as Parkinson defined it. And other studies have shown this kind of optimum temperature somewhere around 14 degrees C for salmon. That lower threshold where, work being done in Alaska showing that temperatures were actually below that lower thermal threshold, that's about 5 degrees or so. You really want to have temperatures warmer than that for salmon. And then when you get even higher, you get into these more critical barriers. So thermal migration barriers, so temperatures that are inhibiting migration of salmon is roughly around 21 degrees C. Know, of course, that all these studies are for different locations, north and south, and so there definitely is some flexibility in these and different results from different studies depending on what basin the research is coming from. And then your maximum, you're getting up towards cardiac failure at around 24.5, 25 degrees C. Critical here is that Atna Lake is likely to remain this thermal refugia, or possibly will. It's currently in a good place. Even with some significant average warming, it's likely to stay within that realm, which is a good thing. Unfortunately, that's likely to be the one kind of key thermal refugia within the larger Morice system. The Morice River is moving up, likely by the end of the century, moving up towards some of these critical species assemblage thresholds where you're giving the your other species are benefiting, preying on the smolts of salmon, etc. And then you start to get up towards those potential thermal migration barriers as well. And know too, just once again, that it's likely that these are perhaps underestimates of what we might see, lending kind of credence to one of my conclusions, which is going to be the need for increased monitoring and observations. All right. I'm going to wrap things up with some kind of high-level conclusions from all of this, and then take some questions. So first of all, we do have current glacier cover to provide some late summer buffering capacity. So a max of about 30% of July to September discharge under current conditions. And that was for the Morice River. Changes in forest cover are likely having some significant impact on snow accumulation and melt. This will be impacting the freshet. Riparian shading ? I don't know from this work, but something that would be important to look into. I'm going to suggest here that more work is definitely needed, both on the question of impacts on snow accumulation and melt, timing of the freshet. Also, this probably offers one of the biggest opportunities for remediation moving forward and in creating the environment that we need moving forward for salmon, for stream temperatures, for maintaining discharge. Rates of glacier recession have doubled in recent years. When looking at future temperature change, a bigger picture here is that we're moving towards a world with longer, more intense melt seasons and shorter, warmer winters. Those shorter, warmer winters are going to result in potential for winter rain events or melt events becoming more common, potentially leading to scouring events in the wintertime, and also impacting the timing of the freshet. We are likely to see some modest precipitation some modest increase in precipitation. This could actually lead to some increased snow accumulations at the highest elevations. All of the modeling work looking forward looks like we're in for dramatic glacier recession. And again, it's this continuation of the the recession rates we're seeing currently that are really quite high. So we're looking at a volume loss of about 75% by mid-century and near total loss of all of the glaciers in the Maurice by 2100, maybe some remnant ice masses remaining. And then in terms of surface area, which is slightly different than volume, we're looking at about 60 to 70% loss by 2050 and then 80 to 100% by 2100. And with that loss of surface area, you get a commensurate loss in meltwater and the buffering capacity within your streams and rivers. We are likely to see declining maximum snowpacks, and this is most critical in these vulnerable low-lying basins. Lamprey and Owen Creek would be particulars in this area. We're likely to see kind of low to moderate reductions by 2050 or so, so maybe 5 to 20% reductions in maximum snowpack by mid-century. This will have impacts on the freshet, but also groundwater recharge. And then also by the end of the century, some of the projections show continued of moderate changes, and some of those high level or highest projections of temperature increase show some pretty dramatic losses of seasonal snowpack of upwards of about 60% reductions in snowpack when you get to those most extreme, 5-6 degrees C of warming in the wintertime. And then lastly, increasing stream temperatures. We definitely need observations and monitoring of this to see where the baseline is and to project where we're likely to go. We may well cross important thermal thresholds in the larger Maurice system within the coming decades. But it's likely as well that some cold water refugia will remain, and Atna Lake being predominant among these. Great, so I haven't left as much time as I would have liked for some questions, but I am happy to stop there and take any questions that you have.
Great, thanks so much, Matt.